Now here in part 4 of 4, we want to look at a more realistic population model. So we're going to use a capital P to represent the population. Your author has a thing for rabbits, so you might want to think in terms of what the textbook says, or rabbits, but this could be any sort of thing. Now the quantity dp dt would represent the rate of growth, the change in population to the change in time. And we'll start off by developing the ideas behind the two quantities that we're going to refer to as the Greek letter beta for birth rate. Notice it's B in both of them, and delta for death rate. So our model would look like this. The rate of change in population is the birth rate minus the death rate, the change in births to the change in deaths. Now we'll start off by making the observation that the death rate we like to think of as a function of the population. So if we have a small population, we're going to have a small death rate. But as the population grows, the death rate also grows. The more things there are, the more disease, the more struggle for food and things. And so we will use a quantity gamma as a constant, and we will write delta equals gamma. We'll use a subscript of D because this gamma is for the deaths, times P. So this would give us a direct relationship between the delta and the P, the constant being the gamma sub D. And so if we substitute that, we know that delta P then would be gamma sub D times P, or gamma times P squared. Now similarly, we observe that the birth rate is also related to the population. However, these are sort of inversely related. If the population is small, the birth rate is going to be a constant birth rate. But as it gets larger, the birth rate decreases. And again, that's because as it gets larger, oftentimes populations have more problem reproducing, and so the rate is going to change by getting smaller. Now here's how we will write that. Our beta is equal to beta naught minus some constant times P. The constant would be a reflection of the particular population. That particular constant for rabbits may not be the same as it is for squirrels or hawks or coyotes or anything like that. However, by substituting that for the beta, we end up with the beta naught, the constant birth rate, minus some constant gamma, this time with the subscript of B, meaning it's not necessarily the same constant as the other one we were doing, times P squared. So substituting those into our differential equation and then doing a little bit of algebra, like factoring out the P squared on the right, and then replacing the gamma sub B plus the gamma sub D with just a gamma, we end up with this. Now again, in our description, the beta naught is the constant birth rate that it would have been in an ideal population. And the gamma, as you can see, is some combination of those two constants together. So a little bit of simplifying, and we can now factor out the gamma and rewrite the beta naught divided by gamma as just some other constant, which we'll call kappa. There's a significance behind the lettering scheme kappa. And so our differential equation would come out looking like this. Now, the constant solutions, remember P is our variable, the population is our variable, the function quantity that we're trying to recover eventually, and the constant solutions would be where gamma times P is equal to 0 and where kappa minus P is equal to 0. So that would give us two constant solutions, P equals 0 and P equals kappa. The P equals 0 is pretty easy to comprehend because all that says is whatever things you're studying, if you start out with 0, you don't have to worry about birth rates or death rates because you're always going to have 0. So that's a constant solution. The other one needs a little thought. By saying that P equals kappa is a constant solution, what we're basically saying is that you'll always end up with a population equal to some constant kappa. Now you can probably comprehend from the differential equation and the constant solution that if kappa is greater than 0, now if you look here at kappa minus P, if kappa is greater than P, then that's going to be positive. And so dP over dt is positive, means there is an increase in the population. So if we start out with a population smaller than the constant kappa, it's going to grow up to the constant kappa. If we start out with a population that's larger than kappa, then kappa minus P will be negative, dP over dt will be negative, and the population will be decreasing. And so the population will be decreasing to the constant kappa. So that's why we refer to the constant kappa as the carrying capacity. This is the population that's sort of ideal for that particular situation. If it's a smaller population, it'll grow to the kappa. If it's a larger population, things will tend to die off until it reaches down to kappa. Solving this differential equations is actually an exercise in your homework, but I'll get you started on it without doing the whole thing for you. You notice here that we have a separable differential equation. So we'll collect all the p's over on the left-hand side and the t's over on the right-hand side. Now the constant gamma could go on either side, so we'll just leave it over here on the right. We integrate both sides with respect to t on the right, p on the left, and we have to do the integral on the left-hand side using the partial fraction decomposition that we studied back in Calculus 2. Here's a brief summary of that. So the left-hand side ends up to be a 1 over k times the integral of 1 over p plus 1 over kappa minus p. The integral of the right-hand side just comes out to be gamma times t. And we'll use the constant of integration over on the right-hand side. To integrate the left-hand side, well, first we'll just get rid of the kappa by multiplying. To integrate the left-hand side, we would have the ln of p plus the ln of kappa minus p, which we can combine together into a single ln, and then do the natural exponential of both sides. Now that's the calculus work for recovering the population function. You just need to take the result that we came up with here, see if you can recover the p function in a format to match what the problem in the book is asking for.